Yeah. My name is Atul. I'm working as a security researcher with a company named the Software Cell. And as you already know, my talk is about binary code. So if you just look at it, this is the agenda for my talk today. I'm going to tell you or to try to understand the concept of virtual machines as well as emulators to show how I implemented what I call as an abstract design and how will it benefit you in the long run as a security researcher, whatever. Now, let's get quickly moving towards virtual machines or emulators. Now, how many of you here have not used a virtual machine? Or maybe I just asked the wrong question. How many of you here have used a virtual machine? Yeah, that's fine. So if you are into the infosec industry and if you haven't used a virtual machine, you are not working hard enough. So, okay, one of the things that I really like about virtual machine is that it's an amazing piece of technology. Can you just name some of the common virtual machine software that we have? VMware, VirtualBox, Virtual PC. Yeah, Chemo. You've tried that. Yeah. So there are lots of them, right? Okay, I'd like to keep this session as much interactive as possible. So if you have some doubts, suggestions, questions, or whatever, just shoot right away. All right. Okay, how exactly does a virtual machine work?
It actually uses the resources currently running in OS.
Right. And what does it do exactly?
It creates a layer on top of the operating system previously. On based on that, it creates a hardware, virtual hardware. Based on top of that, you create your own guest machine.
True. So what is happening is that a virtual machine is a piece of software that is going to emulate hardware. Alright? Like for example, let's take into consideration, for example, I've been seeing a lot of Android relays happening here. So I'm pretty sure most of you have attended it. So what Anand has been doing is that he's been demonstrating how to create applications for the Android platform on the Android emulator. Right? Now, the thing is that this emulator is something that is going to emulate on a host machine. It could be Windows, it could be Linux, it could be anything. On top of that, the emulator is a piece of software that is going to emulate the hardware of an Android platform so that the Android OS can run on it. But the OS, it cannot even recognize whether it's a Windows system or what, because it is being run inside a sandbox kind of a thing that is going to respond exactly the same way as a real hardware would. Right? Like for example, if let's say inside VirtualBox, if I install Windows XP, the OS will never understand that it's been run inside the context of an application. See, an OS has to interact with the hardware in a lot of ways. For example, there are memory input output happening, there are COM, networking stuff, lots of things happening. Now the software has to interpret all of these signals and has to respond accordingly as an actual hardware. That's amazing technology by all means. Now, how easy is it to create one of your own? Has anyone ever tried to write an emulator for any platform? Have you ever used an emulator?
Yes.
Yeah. Apart from Android, anything else? DOS. Yeah, but the emulator.
iOS.
Yeah. Anything else?
PSP.
Pardon?
PSP.
Yeah. Anything else? Like NES? Have you used NES or Game Boy or maybe something like that? Apart from that, there was a recent post by a guy. I don't remember the exact name of the guy though. What he did was that he created an emulator for a platform or an ancient computing technology called as PDP-11. I don't know, exact byte maybe. So that kind. Now these were all run on a platform. Have you actually opened up your gaming console ever? Has anyone tried that?
Sorry.
Have you ever opened up that gaming console or the box that you had, which ran the game for you, to see what is inside it?
No.
Out of frustration, yes.
Okay, I don't think that's something that we can count here, but still. The point is, it is running an 8-bit processor, Most of them, I think, apart from the Sega one, but there was a different section called the Sega one, which was supposed to be more advanced. But apart from that, almost all of the gaming consoles, they ran an 8-bit processor. Amazing, you know. I mean, 8-bit is like really limited technology, but on top of that, they had amazing games like Super Mario. I mean, it's extreme programming to have 8.4 levels with lots of queens to catch and dragons to kill and everything. And it's like amazing programming. On top of that, you could run. It could produce graphics. It could produce sound. It could take input. It could give you output. So basically, if you look at it, it was a computer. Back in those days, you bought a real computer for $500. Has anyone ever tried to use it as a computer? That's sad, right? Because we don't understand the technology that we're surrounded by. Another thing that I recently saw, I was present for the talk here before for the guy who presented before me, and he was talking about embedded devices. And he was talking about how he got a shock when he was trying to test an embedded system live. The point is, if you understand an embedded system and if you have the data sheet for it, you don't really have to test it physically. What you can do is, see, these embedded devices are like very tiny devices, they are not very complex. They have got their own data sheets. What you can do is you can emulate or you can write the code for it at software level and test everything inside out by using your own tools. If you spend at least just a matter of 1 week at the most, you can do that. And you don't have to be jolted by 250 or 220 volts of shock testing that. So I'll tell you what I did. A few months back, I was supposed to design a challenge, a kind of online challenge for a conference that we host. Now, as you already know, there's a challenge going on right now that is named as Nullcon Battle Underground. And then they had an online version of it, Nullcon CTF and stuff like that. Now, these are amazing. I played them, I love them. But I wanted to do something totally different. You know? I didn't want to do a kind of web-based application hacking or stuff where you are limited by certain things. Like, for example, most of the challenges that we observe online, the problem, or basically you can say that it's a problem with web hacking itself or hacking itself. Hacking is something that does not provide 100% guarantee that you can hack into system. Okay? There is always a possibility that it is completely secure. And there is always a possibility that it can be hacked into. But then there is no guarantee that one of them is true. Whereas in terms of reverse engineering, the beauty of it is that no matter how tough or no matter how complex the system is, it can 100% reverse engineer completely, provided we spend some time on it. That's why I love reverse engineering more as compared to hacking. Now, what I did was that I created a challenge wherein you will be provided with the code or the data sheet for an abstract design that I made. Now, to make you understand what exactly happened in the challenge is that, now let's say that I provide you with an Android application, like let's say Hello World application inside Android, okay? And you're supposed to, that is the actual game that you're supposed to play. Now let's say if I provide you that, how are you going to execute on your system? If I provide you with an Android application, for example, like a Hello World application, and you only have a computer, how are you going to run it? You need to get an emulator for that, right? Same concept. So what we did was that we gave them a kind of a game for a design or a platform that I designed. Okay, I designed a complete platform, and I gave them a code which will run only on that particular platform. So if you want to get started with the game, you'll have to write the platform on your own. Are you getting the point? Now, tell me, see, if you look at the Android emulator and an Android Hello World application, which is more complex? The emulator, obviously, right? Now, see, when you're designing an emulator and when you're designing an application, you always have like 3 options basically. One of them is that you can create or you can make the emulator and the code equally complex. Okay. What you can do is you can transfer most of the code or most of the functions on top of the emulator itself for the device or the platform itself, so that writing the code becomes very easy. Because almost all the code is already there. All you have to do is just call certain functions. Or else what you can do is you can keep the platform very simple. But then if you do that, the code has to be outstanding. Are you getting it? Now, here the problem was that I really doubted that a lot of people are into programming and stuff, and frankly, I have no idea as to what is the capability of the guys who interact with me online and stuff like that. So I did not want to make any chances, or I did not want to take any chances. So what I did was that I tried to design a platform that is very simple. Okay? Because I'm going to be providing the challenge. So creating the challenge is going to be my headache. But then to get started with the challenge, you'll have to write the platform itself, right? So I wanted to keep it as simple as possible. So what I did was that I thought of picking up the first versions of like the tiniest microcontrollers that I could get, for example like 8085, 8086 and stuff. Because I know that there are already tools available for that, using which I can create the ROM as a code for it. But trust me, even 8085, if you try to emulate it, it's very tough. It's got a huge instruction set, lots of registers and stuff, so it must be very tough. So I completely chucked it out. Then I tried to even go from PDP-11 that was designed, but then still, I'll tell you one of the reasons for that is that, they have very complex memory mapping systems happening. For example, they have segments and offsets and stuff. So if you want to select a particular memory and stuff, it's going to be very complex, and the processor has to do that. So if I design something on that, you'll end up programming at a very complex level. So I had to sit down with pen and paper, and I had to create a design of my own. Okay, and so what I've done is that, basically every processor has got certain components. For example, it's got registers, it's got a stack, it has got an ALU, and basically that's it, I guess, and some memory operation. And most importantly, every system has got to have its own instruction set, okay, or a data sheet. Now what I did was that I tried to split down every aspect of it to be as simple as possible. Like, the minimum number of registers that you can have is 2, because I need at least 2 to make a swap or an exchange and stuff. So I kept the general purpose registers count to 2. The stack was technically supposed to be only 256 bytes, and the entire design was supposed to be 8-bit. Now 8-bit is 1 byte. Okay, I did not offer 16-bit because if I did that, then what will happen is that once you go beyond the 1 byte limitation, once you're handling with 2 bytes, 16 bits or 32 bits, the problem is that byte ordering comes into play. For example, there's little endianness, big endianness and stuff. So it will become very complex to write a code, which I did not want. So what I did was I stuck with the 8-bit architecture. The problems associated with my very simple design was that I was completely limited when it came to writing code for the code. I mean, this was just a design that I had to make. But then I was supposed to create an entire challenge based on this, right? So I was the guy who was supposed to write the code. I was seriously limited by all these things that I've done. Now, I've posted everything that I've done with respect to the project at this particular GIT location, so you can download that if you want. Shall I move on? Okay, so before we continue with this, what I'll do is I'll just show you the data sheet that I created for this one. Alright, so this is how a normal processor's data sheet will look like. Okay, I'm just going to flip it here. Now, no matter which processor you buy, whether it's an Intel processor, whether it's an AMD processor, ARM, Atmega, whatever, every processor will have its own data sheet or instruction set, because that's how you know how to program a device. Now, not just a processor, I basically don't understand the difference between a microcontroller and a processor, because for me, both of them, they execute code. And as long as they execute code, it's a processor for me. So, embedded devices and everything, this thing falls under the same category. Now almost every processor has got to have a set of registers and a set of instructions, code, or instruction, basically it's called as opcodes, which stands for operational codes. Now if you look at it, it just has got 2 general purpose registers, A and B. It has got a stack size of 2 to 6 bytes. We need to have a pointer or a register named as instruction pointer so that we can keep a track of which code to execute next. A stack pointer to point on the stack. The flag register to maintain certain things like operations and stuff. Now, these are the instructions that I have for the architecture. Okay, I have to sit down and manually I have to design all of these. Now, I'll give you a practical example of how to understand this thing. Okay, let's say that you are provided with a data sheet of any processor that you have. how to manually make sense of it. Now, if you look at this thing, it's exactly the same as any other data sheet. So if you just look at it, now let's say that I want to print a character named A, and A onto the screen using this process. So then what should I do? Or what are the steps that I can take to understand how to get it done? So what I do is, I just check the entire instruction set. I mean, every instruction set needs to have its own, output command, input output command. Now in this case, I have already named one, and it's called this is the command output. Okay, and if you just look at it, the size of it is 1 byte. And what does it do? How well, I mean, it's visible to all of you, right? Yeah. So you print 1 byte from the stack. It's like, I know many people don't like the concept of pointers, but then that's what this is. It's like, you have a stack, and then there's a stack pointer, which is like constantly moving up and down based on other operational stuff. So what this command will do is that it will print the character where the stack pointer is pointing to on the stack. Okay? To any offset, it will just fetch the code. It's like the ASCII code for that, and it will print it out. Now, let's say that my objective is to print A. So what I'll do is let's start to write the code a little bit. Okay, now this one is a single byte or a single instruction. It doesn't require parameters or stuff. Agree? Yeah. So what we are doing is we are going backwards, because I want to print it, so I'll just try to understand it backwards. Now, output will do what? It will print the ASCII or the character that is being pointed to by the stack pointer. Now, obviously, I have to put something onto the stack. Now, let's check if there is some instruction that does that. Okay, this one looks interesting. If I take this instruction, what will it do? These two.
Move the stack point.
Move the center cursor.
Yeah. Okay. So I can move, if I use the output 15, it will be what? Move the value inside A onto the stack. And if I use B, it will move the value inside B onto the stack. So now let's just select move SP, A for the time being. Or maybe let's take B. Now I'll have to put some value to B. Okay, anyway, what is the ASCII code in decimal for A?
65.
This one? So technically, if you observe, according to this architecture, this thing should give me an output of B. Okay, 65, 8, correct. Now, this is what kind of code is this?
Assembly.
This is assembly code, right? Now tell me, what is the difference between assembly code and machine language?
Machine language
is typing.
So is assembly language and machine language different?
Yes.
How exactly?
Processor understands and converts it to the binary language, which is fed into the circuit, which emulates all the circuit.
In assembly, the opcodes are changed to
This is only machine this is not actual.
Yeah, that's what. See, the point is, machine language and assembly language are both the same. Okay? Technically, they are the same. The problem is that we cannot understand it. We find it very difficult to understand ones and zeros. So what they do is that they take collection of the first 8 bits, which is like 1 byte, and they call it as an opcode. So what I'm doing technically here is that this is equivalent to writing assembly code. I'll show you how to do that, for example. Now, if I go back, what is the last, this time we start right to the top. Now there's another instruction that is called as halt, which will stop the execution. Okay? Now, if I want to write opcode for this, how will I do that? Okay? First of all, I'll have to move to this instruction, which is called B, C. B, 65, which is this one. Agreed?
Yeah.
Visible? Now what is the opcode for that? 1B. And what does the description say? The size of the opcode is 2 bytes. Now the first byte has to be the opcode, and the next byte has to be the number that has to be put inside B. Okay. So in this case, you have to consider now. Note that this thing is completely hexadecimal. Okay, it's hexadecimal. Now if I go back here, it is 1B, and okay, now 65 is in decimals, so in hexadecimal it will be like 44, I think. 41. Okay, now what next? The next one is what? Move SP, comma B, right? And I have to just go there. Now I have to check that out, which is this one. Has to be 16. So we'll just follow it by 16. Okay, and then what? Output. This is output 3A. And then has to be Hall, right? Which is 3C. 3C. Okay? Understood so far? Have you followed? Alright. Now what I'm going to do is, now let's compile this code. You know, it's an ASM code. Now what I'm going to do is I'm just going to comment out this part. I'm going to save it somewhere. I'm just going to save it. I'm just going to save it inside a CTM folder and I'm just going to call it, let's say, nullcon.asm. I've saved it. Now, what I've done is that I've written an assembler for this. I'll explain to you how I wrote it though. Now, it will compile this particular code into a, executable for this platform, and then we can try to execute it. Now, based on the specification that is provided, we'll have to write a platform code for it, or the emulator for that. Now, I'll show you the code of the emulator first. I've written this thing in both C as well as Perl, and it's quite easy actually. This is the C code of it, and that's it. I mean, see, if you observe, this is like the main part of it. This part, it's the main, it's just output and stuff. I'm just opening the file, I mean, whatever boot ROM I'm provided with, I have to open it, read it. That's the only part that this thing is concerned with. If you observe, the actual processing happens here. Run. The run function does the actual processing, and trust me, it's not really complex. It is not really complex. Okay? Because you just have to follow this. Everything is given, like I is equal to RT minus X. You just have to convert this algorithm into code. That's it. It's quite easy. Now once you do that, you will have the processor which can execute code which belongs to this particular architecture. Okay? Now, let's compile this thing. The code that we just now wrote. So what I'll do is I'll just, is it visible? This is the compiler that I wrote for this. I'll have to specify the name of the file that I just created, which is nullcon.asm, and I'll have to specify an output file. I'll just call it as bootrom.txt. Okay? Now it says that compiled it, right? How many lines of code? 11, because it's counting all the lines of code. And it says it's done. Now if you just observe, this is the file. Okay, this is the file that I just now created. Now let's try to run this thing. If I just start a processor, it should load that file and it should execute it. Now once I do that, is it visible? Yeah. It is printing A and it is halting, you know. There is no crash, nothing, the code is working perfectly fine. Now what we'll do is we'll try to open the boot ROM or the binary that we just now created inside hex editor and look at the contents. And let's look at what we calculated earlier. Okay. Okay. Nothing is same. Navi 41, 16, 3836. It is exactly the same, right? So the idea is that you have understood by just looking at a data sheet of a processor or any architecture how to create the code. I think you can write a processor or an emulator for that. Is it tough? It's not tough. Trust me, it's not tough. It's tedious, but it's not tough. There's no rocket science involved in it. It is quite easy, quite possible. Can you write, if you can write a processor for it, can you write a debugger for it? What is a debugger? Debugger is nothing but something that is going to just execute the code line by line, and it will allow you to set breakpoints, look at the content of the registers and the stack, wherever possible. Right? Now, how to write an assembler for this? Okay, so there are multiple problems attached with writing an assembler, because assembler is something that has to take assembly code and then convert it into the binary. So when I first started, see, I had to create a challenge, and this is like, I was designing the platform, and initially I was playing around and I was actually constructing binaries using hex editor, because it was fun. I'm creating and typing stuff in the hex editor and it gets executed, and it prints A, B, C on the screen. I was like, really, this is cool, man. And then later what happened was that I thought, okay, now this is not going to work because I'm supposed to write an entire challenge, so this is not going to work. I have to come up with an assembler for it so that it becomes easy for me to write code. So what I did was that initially the first version of it looked something like this. This is the assembler that I wrote for it. Again, see, if you just observe what it is doing is that if I type move A, S2, it completely rejects. It will take, based on regular expressions, it will compare strings and everything, and it will simply replace the numbers, and that's it. And it's going to construct the binary just like we saw how we constructed. Okay? So this is the basic assembler that I wrote, but then this doesn't support labels. Okay? For example, if I want to make a jump to a particular location, like for example, if I want to jump 5 steps ahead, I'll have to write the exact offset manually. Okay? Now that is going to be very tedious. That's when I thought, okay, now this is not tricky. See, another problem attached to that is that I cannot jump a location that is higher than 256 bytes or 256 number, because technically my processor is limited to 8 bits. And if I want to store a number larger than 256, then I'll have to use 2 bytes, right? So it means that my neutron will be corrupted. So I cannot technically make a jump beyond 256 byte or location. So what I have to do is that I have to divide the entire code into chunks. I have to place multiple jumps here and there. Okay. Now, this is one part of it. Secondly, I had to write code. I had to write label handling, or I had to add more features to the assembler. Finally, when it turned out to be a 3-pass assembly. What this means is that during the first round, it will find all the labels that I make, okay, or the location. For example, I can just use a particular, I hope you understand what's a label, right? So based on that, what I've done is that my assembler can handle labels, it can jump to locations and stuff. So during the first pass, what it will do is that it will identify all the labels that are present. During the second pass, it will calculate the offsets and stuff, where it's supposed to jump from the current location and stuff. In the third pass, it will compile the exact binary out of that. Okay, it is still fairly easy if you look at it.
It was a 16-bit processor, there was no need for it to be a 3-pass, right?
Right.
It would have been a normal 2-pass.
True, but then the problem is that in that case, the processor architecture would have been much complex.
Yeah.
But then even then, I'm limited to 64K. Are you getting it? So if I want to jump to a location that is higher than 65535, I'll have to go into this. And that's the only reason why people went into the segment and offset model back in the day. Now this is the code. I mean, this is nothing new. I'm just using the same thing again and again. On top of that, I'm simply adding a few code that will fix label addresses and stuff. You can study the code, it's posted online. And this is how it works. And okay, so the final output of the challenge was this. The size of the ASM file is about 906 KB. And we just want to look at the code. Okay, how many of you have tried brain fog? That's it? Brain fog. Don't mind, I'm sorry for the language. It's the name of the programming language actually. It's called as brain F star star star. Okay. Now that is what we call as an esoteric language. Okay. It's more like it's a Turing complete language, which means that it's complete language, but then it's more like it's not something that you can use practically to write applications. It's just a theory kind of a thing in which you can write code and it works. For example, I'll just give you a demo. I'll just show you the code that I wrote for level 4. This was the code of the final level of my challenge. It looks like this. Okay? And this is what is called as brain fog. This is the brain fog code. And this is how it looks like. Now, on Ubuntu, if you are using Ubuntu, there's a brain fog compiler or an interpreter provided in the repos, which you can use directly. So if you want to see how this code looks like when it's executed, what you can do is just go back. Okay. The name of the compiler is, or the interpreter is BF. Is it visible? This is how it looks like. It's there in the Ubuntu repositories, or you can find it online. It's available for Windows as well as Linux. On every platform it's available. Now what I'll do is I'll just run this code. The name of the file is l4.pf, and I'll just run it. When I execute this code, this is what it prints. Can you see? It is asking for a name. When I enter something, it is asking for a serial, and I have to enter the correct serial combination for that. Something. And then when I enter, it didn't work because that is not the right combination for that. Now if you want to look at actual algorithm, which is behind this brain fog code, you can just I'll just show it to you. This is it. Okay. Sorry, this is level 3 and 4 bit. This one. This is the code. Okay. And this thing, when compiled or converted to brain fog, looks like this. So you'll have to sit manually, and it's quite complex now. It's brain fog is nothing but pointers and stuff, only pointers, and one instruction to output the character and one instruction to take an input. It's quite complex. So I had to sit down and manually write the entire code. Now once you do that, if you just want to see if it works or not, actually, what you can do is you can just compile this one. I'm just going to kill it. I'm just going to compile this one. Okay, I can compile it as keygen. Now if I run it, so if you enter something, this is what I enter. Okay, and this is the password that was generated. This one. Okay. Now I'm just going to copy this one. I'm going to again run the brain fog code that I wrote. It's working fine, right? So this was the level 4 challenge of it. Okay. So basically what I did was that inside a virtual machine named as the AOD architecture, I created another virtual machine that's called as the brain fog interpreter, and on top of that I wrote an entire factory in brain fog. It was running on top of that. So it's like, if you want to practice thing, you have to first bypass the first level, then get into level 4, where you have to even identify that this is a brain fog interpreter in the first place. And then once that is done, you'll have to download or extract the brain fog code out of it. Even then, there are no tools that can help you in reversing this. You will have to sit and manually do it. But then, if you look at the code, now look at the code and think from the point of view of a reverser. Can you find a way to easily crack this one?
You enter simple, I think the password will be much easier to enter.
That's true. Anything else? Now let's say that you are supposed to crack it or find the correct combination. Now you are thinking from the point of view of a programmer.
Right.
Is it visible? Take some time to compile it actually. Okay, it's done. Now if I just run the game, this is how it will look like. And I'm supposed to enter, and this is how the game actually starts. Now if I just click enter, supposed to enter the username, I can use guest. And I'm landed at a complete prompt. If I just type down, there are multiple stuff. I mean, it says run, log out, whatever. If I try something else, it will give me another. So it's like a complete emulated Linux terminal for you. And then you can run the game. You just type run. You don't even recognize that this is running inside a virtual machine kind of a thing that I wrote. Okay, and this is like level 1. Welcome to the channel. It gives you a rough idea of what you're supposed to do and stuff like that. It gives some really stupid hints because the first one was based on patching. There are multiple kinds of techniques that go inside reverse engineering, some of them like patching, lots of stuff actually, serial phishing and stuff like that. So the level 1 was based on patching, level 2 was based on serial phishing, level 3 was based on, so different stuff. Now, the beauty of this is that you have the code, you are the one who wrote the processor, so you understand things inside out, right? There are multiple ways of hacking into this. Multiple ways. You're not limited by just one method. You can use any method that comes to your mind. You're only limited by your own imagination. You're trying to solve this problem. Now, the beauty of this is that if you just look at it, see what's compiled, the size of the file is around 130 KB. Okay? Now let me tell you what all has gone into this 130 KB output that we got. It contains 4 levels. It contains 2 Easter eggs, out of which one is a brainfuck interpreter itself. The other one has basically included this file which is called as surprise.rar. Okay? It contains, if you just look at the content of it, it contains an actual malware which we extracted from 40 Hex magazine as a tribute to them. It's a very famous malware called as ambulance. After that, I have included the assembler that I used for it. I've included the code of the challenge to level 3. Inside the challenge itself, to level 3. There are 2 implementations of the processor, one in C, the other one in Perl. And I've even included a test ASL so that if someone is willing to write some code in that, you can just follow it. It's a complete tutorial kind of a thing. And everything, all this is gone into the boot ROM that was generated by you. So this is 130 KB and that is art. It was amazing. It's a pretty good experience. Now, I'll quickly wind up the entire thing. Okay. So how will this thing benefit you? You've understood how to read processor instruction sets, how to read data sheets. You understood how to write an assembler, how to write a basic debugger for yourself. You can literally reverse engineer any platform's code now. But this is the basic that goes into any platform, whether it's embedded system, any kind of processor. As long as you are provided with the data set or the instruction set of it, you can write assembler, you can write a debugger, you can reverse that code. That's the beauty of it. So that's all. Crash. Okay, so that's my contact information. If you guys want to contact me, any questions, doubts, queries, anything?
Somebody uses as a collection scheme kind of scheme.
Yeah.
What about the resources if it's an actual processor? I mean, this was an 8-bit processor.
Right.
Say if you go to 16 or 32 or something like that, and if you're running actually on top of it, all your own processor like that. What are the resources that you use? I mean, how resource hungry will be?
It will completely depend upon your implementation. For example, there are many copy protection schemes even now that employ around 6 VMs inside them. Yeah, 6 virtual machines inside the DXE. It's like, different parts of the code get executed by different VMs and it's very complex to reverse it. So it will depend completely upon you.
So have you seen any kind of malware actually utilizing this kind of concept where the processor becomes the main process and the plugins are actually binary files that the processor executes?
As of now, I haven't seen anything that is utilized something like that. Besides, I haven't even seen something that uses a VM inside a VM. I don't know. But then I think that's quite possible. I haven't seen any yet. Any other questions, doubts?
How about dropping this processor in a machine, which doesn't have any malicious function in it and everything. And then after that, you push your binary code into that processor, for which you don't have debugger, assembler, no clue about it. So how about that concept of maybe a two-stage malware?
That is possible because when you're uploading this particular binary which doesn't belong to the regular opcodes of an Intel processor or something, the antivirus is definitely going to be defeated as long as there is no byte or pattern that matches some other malware signature. That is one thing, but then the basic flaw in the design is that every malware needs to connect back. There are certain tasks which are flagged as blacklisted. For example, it has to connect back, or if any process tries to connect back to you or connects to a particular port on a different, or opens a port on your system, it is flagged by the antivirus or the firewall. So it can work as a standalone application on the system, no doubt. But then the moment it tries to do a reverse connect or something, it will be flagged.
I mean, there can be another mechanism, but the point is the concept can work.
It can work.
Right? But the only transfer of files is the issue, which can
Right.
be sorted out in a different.
Right, that's what.
Implanting it as a service or a device driver itself is no issue.
How do you make it run, that processor?
Not to run for every boot.
I think that's possible. Anything is possible, especially with Mitchell. Anything is
I
possible.
don't see heuristics actually.
Yeah. Anything else? Yeah.
Here's my hard disk. Just kidding.
All right. So I think that's it. Thank you so much.